Hello everyone. In this lecture, we will study the properties of unilateral Laplace transform. These properties are similar to those of Fourier transform. This lecture will study these properties. First, the linearity property. This is similar to that of Fourier transform. The second is the time shift property. This is a relation between input time domain signal and the complex frequency domain function. Here is some application for these properties. Signal xt is represented as this expression. This is the picture of the signal. We have now step signal u of t, its Laplace transform is 1 over s. So according to time shift property, you can get this signal and we can get the Laplace transform for this signal. According to the linearity property, we can get u of t minus u of t minus 1. Its unilateral Laplace transform is this expression. Because this signal is a finite duration signal, its region of convergence includes entire S-plane. This is another signal. A signal can be represented as this expression. We have the Laplace transform for rainbow signal. So according to linearity and the time shift property, we can get the unilateral Laplace transform for this signal. Similarly, this signal is a finite duration signal. Its region of convergence includes the entire S-plane. For another example, to find the unilateral Laplace transform for this signal, first we will discuss the x1 of t to find its unilateral Laplace transform. Xt can be represented by x1t in this way. Here, t equals 2. First, we will find the unilateral Laplace transform for the x1t. Then we use the properties of linearity and the time shift. We can get the xs. From this equation, we can get this expression formula. Now we will find the x1s. This is x1 of t. We can find its unilateral Laplace transform for x1 of t. Here, its region of convergence includes the entire S-plane. So we can get the x of t, its unilateral Laplace transform is in this expression. Another property is scaling property. Here, the a is greater than 0. This is the convolution property. It means the signal convolution in time domain corresponding is Laplace transform multiplication in S domain. Here is the application for this property. This signal can be represented as the convolution of x1t and for the x1 of t, we can find its unilateral Laplace transform. So, according to the convolution property, we can get the Laplace transform for this signal. Similarly, the signal is a finite duration signal. Its region of convergence includes the entire S-plane. This is the multiplication property. It means the signal multiplication in time domain. The Laplace transform is the convolution in S domain. This is the exponential weighting property. It's also termed the S domain shift property. This is the relation between the signal and its Laplace transform. For example, determine the unilateral Laplace transform of xt. Here, alpha is a real number. We have known a cosine signal its unilateral Laplace transform is defined in this formula. According to the exponential weighting property, we can get the Laplace transform for this signal equals this formula. This is another property called linear weighting property. It's also termed S-domain differentiation property. It means multiplication by minus t in time domain corresponding to differentiation in S domain for its Laplace transform. For example, determine this signal's unilateral Laplace transform. Here, a is positive number. We have known for the step signal, its unilateral Laplace transform is 1 over Cs. According to the linear weighting property, we can get the Laplace transform for ramp signal. Applying the property again and again, we can derive this result. For the exponential signal, we have known its unilateral Laplace transform. According to the linear weighting property, we can get the Laplace transform for this signal. Applying the property again and again, we can get the Laplace transform for this signal. Another property is the differentiation property. This property is very important for solving the differential equation. this is a verification procedure. Applying the property repeatedly, we can get this formula and this formula. The property is useful to solve the differential equation. We'll study it later. For the ramp signal, we have now its Laplace transform is 1 over s squared. The step signal, we can get the step signal by differentiation from ramp signal. We can find this Laplace transform is 1 over s. Similarly, we can find the Laplace transform of delta t is 1. And furtherly, we can get this result. For example, determine the unilateral Laplace transform of signal xt by the differentiation property. We can get this signal and this signal. We have, according to the differentiation property, we have this equation. Because this is 0 and this is 0, so we can get this result. From this signal, we can get the unilateral Laplace transform equals this expression. So we can get the Laplace transform of the signal equals this expression. Because this signal is a finite duration signal, its region of convergence includes the entire S plane. According to the property, we can get the model in S domain for inductor. Another property is integration property. This is a relationship between the signal in time domain and the Laplace transform in S domain. If this condition is satisfied, we can get this formula. For example, determine the unilateral Laplace transform of this signal. This signal x of t can be expressed in yt. This is a yt signal. The yt can be expressed in these step signals. We have now this condition is satisfied. So we can get the unilateral Laplace transform for y of t. According to the integration property, you can get the unilateral Laplace transform of this signal equals this expression. Similarly, we can get the model in S domain for capacitor. Finally, is the initial and final value theorems. If the order of the numerator polynomial is less than the order of the denominator polynomial in x of s, the initial value theorem states that we can, from this theorem, we can find the x value at t equals 0. Similarly, we can get the final value of xt according to this equation. Here is the example. Because x of s is a proper rational function, so we can directly apply initial value theorem. Can get this initial value. Because the region of convergence of s times xs includes j omega x's in s-plane, so we can directly apply the final value theorem. We can get the final value of xt. Here is another example. X of s is an improper rational fraction, so we cannot directly apply the initial value theorem. First, we'll convert this function into a proper rational fraction. Then we can use the initial value theorem to find the initial value for the signal. The region of convergence of x times xs includes j omega x's. So we can use the final value theorem, get the final value for the signal. In this lecture, we have studied the properties of unilateral Laplace transform. That's all for today. See you later.